So how do we work out moments around a point? Well, we know that a moment is a force times a perpendicular distance. The most straightforward moment that we can show here is if we had a force here and a distance d here, that the moment due to this force around P would be, I'll call it like force 1 times distance, because that force is multiplied by its perpendicular distance back to the point where we're calculating the moment. And because it's counterclockwise, it's positive. However, often we don't have a nice perpendicular force. We actually have a force that's oblique to the plane. And we know the angle, and we're given the force. How do then we work out the moment of this force around P? Well, what we can do is remember that this force has a line of action. Okay. And that line of action can be broken into, it can be used as a diagonal, where you can draw a parallelogram around that diagonal that takes you back to the original point, and that parallelogram has two sides, one that defines the vertical component of the force and one that decides the horizontal component of the force. And we know from trigonometry that that angle there is the same as that angle there, is the same as that angle there. So we know that this vertical component here is F sine theta, because this is F along here, this is F sine theta. And we know here that this is F cos theta, but we're not going to use it because it's acting along the moment arm, and any force acting along the moment arm has no perpendicular distance back to the point. However, this one has a perpendicular distance back to the point, and its distance is d. So the moment due to this particular component here is F sine theta times the distance d back to the point. And once again, because it's in the counterclockwise direction, it's positive. Now you can work that same moment out in two different ways. We just did it using the two components. You can also, sometimes due to circumstances of your problem, you don't want to use the components, you want to use the original force. So you can take that line of action all the way along here until you can find the perpendicular distance from that force back to the point P, which is where you're calculating the moment around. Because a moment is a force times a perpendicular distance, we can now take this force times this perpendicular distance. So this time we don't have to calculate F because we know what F is, but we have to calculate the moment arm. And here we know from trigonometry that this is d sine theta, is the length of this arm here. So the moment calculating around the moment around P, using this method, we take force times its perpendicular distance. So that is F times d sine theta, which is the same if we just rearrange F sine theta times d. And once again, it's going that way, so it's going around the point in the positive direction. So we can see in both cases we end up with the same value for the moment, F sine theta times d. And this is to show that you can calculate it two ways. You can either take the original force, and at the point it makes contact with the bar or the beam, you can divide it into its vertical and horizontal components, and then use the vertical component times the length of the beam, or you can take the force along its line of action and calculate the perpendicular distance back to the point. And in either case you get F sine theta times d. We can see that this horizontal component, which we'll call the horizontal force, is actually F cos theta. and we can see that the vertical force is equal to F sine theta. Then the complex part often comes when we're trying to work out where are the moment arms back to this point. How do we see those? Well, what we do is remember that each of the forces that we're looking at now that are making up the moment have a line of action. So we can draw the line of action for the horizontal component, and it has a perpendicular distance from that line of action back to the pivot point, and that's the distance. We'll call it DH because it is the perpendicular arm for the horizontal component. Just say we know that this angle here is alpha, well then we know that angle there is alpha, well then we know that this would be D sine alpha. Similarly, for the vertical component, we take its line of action, and from that line of action we take a perpendicular back to the pivot point, and we'll call that distance there, that moment arm is the moment arm for the vertical, and it is D cos alpha. So that's a trick in finding those moment arms. You take the line of action and then take the distance from the line of action, which is perpendicular, back to the pivot point. So the sum of the moments for this system will be the vertical moment plus the horizontal moment. In this case, in each is force times distance. So here we have for the vertical, F sine theta times vertical times its perpendicular distance, which is D cos alpha. And for the horizontal force, we have F cos theta there times its perpendicular distance, which is D sine alpha. Sometimes you might be given those distances there, but if not, you can use trigonometry to work them out. So you can see in an oblique system you need to work out both the components of the force and the components of the distance to get the moment arms in order to work out the total moments. In this case, because they're both in the counterclockwise direction, they're both positive.